Okay, in this video I'd like to continue the discussion of ROADMs, that is reconfigurable optical add-drop multiplexers. And in the previous video I was talking about chapter 10 in the ONS 15454 configuration guide. And in chapter 10 we did talk about these ROADM devices, and in particular the most important one I feel is this 32 or 40 channel wavelength selective switch, in which we have two arrayed waveguide gratings, two AWG devices facing each other. One is a DMUX and one is a MUX. And in between we have the ability to add channels using 1x2 switches to monitor the power on the add channel using photodiodes, to have VOAs on every channel, variable optical attenuators, to equalize the powers, and also photodiodes to measure those powers as we go. And so the basic idea here is this is an add-drop multiplexer. On the input of this device you have an optical splitter which allows you to drop, sending the drop signal with all of the wavelengths onto a DMUX, and then you reroute that around to the input of the AWG, and here's where you can add. So you have to drop a channel before you can add a channel. So that was the WSS, but what I've got here now is a data sheet on these devices. And so it actually shows you the picture of the device, not just the engineering drawing of the front plate. So we have the 40 channel wavelength cross connect, we have the 40 channel wavelength selective switch, 40 channel multiplexer, and a 40 channel demultiplexer. And basically what this document does is it gives us a couple of nice pictures to look at to see how these things all work together. First of all, is this picture is really small and it doesn't help to blow it up, unfortunately. This is a picture of the Cisco software, which is used for provisioning these systems. And on this you can see a graphical representation of the 15454 platform with the various cards in it. I believe the card that is highlighted here is the one where we have data showing below here. And in fact, I believe that what they're showing, although I can't read it, is a couple of add wavelengths, and then this is the wavelengths that are being passed through the system as express channels. That is neither adding nor dropping. That's called an express wavelength. And so basically you can use software to provision and control all of the things that are going on these cards. But the real point here is this diagram. This diagram shows you how to create what's called a ROADM node. This is a degree 2 ROADM node with 80 channels on it. And let's see if I can talk you through this. First of all, we have the amplifier booster, the BST, the optical amplifier booster. So there's an EDFA here, but there's also this splitter, which splits off the optical service channel, and that's what the OSC monitor does here. So we put the OPT BST right here at the input, okay, and it drops our service channel and then sends the rest of the wavelengths into an optical amplifier with inline or mid-stage access to dispersion compensation units. And then it goes to the 40 channel wavelength selective switch. And as I showed in this in the previous picture just now, the first thing that it does on the input to the wavelength selective switch is have a splitter, and that's right here. And that is, let's see if I can find the picture, the same splitter here we go. basically on the 40 WSS device, we have the input here, and then there's that splitter. Okay, and that's what is shown right here, and that splitter takes us off to a 40 channel demultiplexer. Okay, and the rest of that signal goes on through, and that goes into another 40 channel wavelength selective switch. But here we're going to go in on the channel add part of it. That is, we're going to go in on this part coming up here into the two facing AWGs. And at this point we demultiplex all the optical channels. We have 1x2 switches on every one of those channels that allows us to switch in the input where we're adding channels. So this is where channels are added, and then we've got VOAs and photodiodes to monitor those channels. The output of that goes straight into an optical booster amplifier, and right after the optical booster amplifier we mux back in the optical service channel. And so this is one complete directional pass through this ROTEM node. Okay, it allows us to have drops from this demultiplexer, and it allows us to have adds in between the two AWGs. Now the way these cards are all set up, they each have a transmit and a receive section, and so they work together. If you put two wavelength selective switches together next to each other, instead of, sort of the picture I drew earlier, here it is, on the 32 channel device, the picture I sort of drew earlier was that you come in first and then you loop around, and first you do your drop, and then you loop it back through and you do your add. Now you could do that, you could loop through on one card, but the way it's set up, you can put two cards back to back, and the output of one is the input. The output of one part of one is the input to the other part of the other. And so now let's go the other way. Coming in from the west side, or from the east side, we have again an optical preamplifier with mid-stage dispersion compensation. We go into the 40 channel wavelength selective switch. We have our tap, which comes off to demux for channel drop, pass through to the other wavelength selective switch where we have the opportunity to add channels, and then on out through another booster amplifier, and then we multiplex the optical service channel back into it. So this is called a degree 2 ROTEM node because it has bidirectional optical add and drop, and it's a great thing. The main drawback so you can drop any channels, any combination of the 40 channels you want, and then add in new information onto those channels, and it works in both directions. The main limitation of this device is that each of these output fibers from the demux is channel specific. You can only get one wavelength out of those fibers. Same thing on the add channels. You have to add the right wavelength on the right piece of fiber, or else it won't work. Okay, so hopefully that helps describe these things. The next diagram, well, I'm going to draw some diagrams by hand, but basically what you do is you create some ring structures, okay, and you put these things at each node. Okay, so you can see here we have a wavelength cross-connect switch with a mux and a demux, and you can add and drop channels from each of these nodes in this great big ring. Let me draw just a quick sketch for you on optical add drop channel plans and node and ring structures. I'll try not to make the video too long here, but basically if you have an optical ring with 4 nodes on it, okay, and each of them has that node structure that we just went over, this degree 2 node, Okay, if each of them has this degree 2 node, then we've got bidirectional and we've got add and drop multiplexing capabilities. And what that allows us to do is it allows us to make a ring, first of all, and it allows us to make a bidirectional ring where we have one set of information circulating clockwise and another set circulating counterclockwise. And in fact, these are redundant sets of information. This allows us to do protection switching. Okay, this if we have this bidirectional ring. Actually, what I want to talk about here, I want to just consider a simpler case of a unidirectional ring with 40 wavelengths on it. Okay, this ring structure allows us to have adjacent rings to it. Okay, and these rings can then be used to create a very complex topology. So, for example, we could provision, and this is why these are metro type situations, because there's always a lot of customers in the metro and they always want to change around how much bandwidth they're getting. And so, for example, if we want to add lambda 1 here, we could provision lambda 1 so that it goes from here to here and then over and then around, and it then gets dropped here. Okay, if, let me get some different colors here, if we now want to reuse lambda 1, we can add lambda 1 here and use it to go around like this. And so what we're talking about having is wavelength reuse. Okay, this wavelength, lambda 1, was dropped at this node, and then a different signal with lambda 1 was added at that node. Okay, and this wavelength reuse makes for a lot of very efficient type of bandwidth utilization. Okay, and there's a lot of software involved with figuring out, do we have a wavelength that goes from point A to point B on our network? Okay, we don't have in this node design, we don't have the opportunity to switch from one wavelength to another. We've got to keep lambda 1 through the whole path. And so, you know, it's an interesting problem to try to figure out whether or not there is a wavelength from point A to point B. In any case, these wavelength add-drop multiplexers allow for flexible use of all the bandwidth in these ring structures. Okay, thanks.